All right, this is Mr. McCord's AP Chemistry class, and we are continuing on with equilibrium. Okay, to recap some stuff we've looked at with calculating equilibrium constants. Okay, we showed that setting up an equilibrium constant is essentially our products over our reactants raised to the power of their coefficients in the chemical reaction equations. Okay, so this is something AP wants us to be able to do. We should be able to figure out what an equilibrium constant is just by plugging in concentrations or partial pressures at equilibrium. That's an important part. Sometimes they will give you initial concentrations that we need to figure out how they change to equilibrium. We do a little ICE table, we call it, ICE, so I for initial, C for change, E for equilibrium. When we're lucky, they just give us the concentrations or partial pressures when it's at equilibrium, so we just plug the numbers right in. Okay, now as a reminder, we can do an equilibrium constant expression for really any type of reaction as long as it is reversible, as long as it can reach equilibrium. And that constant, either Kc or Kp, is going to be the same number for that reaction at that temperature. So in this example over here on the right, we're looking at N2 and H2 reacting to make NH3 and then going back the other way. We did this example in a past video. Okay, so typically our equilibrium constant is our products over our reactants raised to the power of their coefficients. In this case, we're using pressures, so specifically we might call this a Kp. So we're using the partial pressure of each of the gases involved. Now all I have to do is plug in the partial pressures of each of these, and I can get a value of the Kp under these conditions. 0.166 squared divided by quantity of 2.46 times 7.38 to the third power in quantity. Okay, what I get here is about 0.0000279 with no units. Okay, now typically the values of equilibrium constants that we get tend to be either very, very big or very, very small. So I want to move my decimal point to be right after the first actual number that's not a zero. Right? I still want it to be the same value. So I need to multiply it by 10 to the something to put the decimal point kind of back where it belongs. Right? So under these conditions, my Kp is 2.79 times 10 to the negative fifth-ish, something around there. So whether we start with, this amount of N2 or this amount of H2 doesn't really matter. The equilibrium that we reach using the partial pressures should give us this number. Okay, so I could start the conditions out in a couple different ways. I could have a little bit of these reactants and no product. I could have a lot of product and no reactants. I could have a little bit of each or a lot of each, but we'll settle here as long as we're at 472 degrees Celsius. This ratio of products to reactants will come out the same. And that's kind of the beauty of the equilibrium. Now, if we do change the temperature, then we get a different Kp. We would have different pressure values because the equilibrium is now different. It's under different conditions. The way that the reaction operates and how things bump into each other, how easy it is for our reactants to change into products or vice versa, is dependent on that temperature. So we should expect our equilibrium constant to be different at different temperatures. Okay. Also, just as a note, if you were very careful at reading the slides and stuff before, I believe I had this kind of turned around with the products on the left and the reactants on the right. It's now corrected. So I think I had the products on top and the reactants on bottom, which was correct, but this was kind of turned around. I might have had my letters wrong for my exponents for this example. Okay, so this is just another example of evaluating our Kc value. So I like using this N2O4 and NO2 reaction as an example, and pretty much everyone in chemistry education does, because it's a very visual demonstration that you can do in a classroom if you've got a tube of N2O4 and NO2 together, because of the color change that happens at different temperatures as you shift around the equilibrium. Okay, so at this temperature, we're keeping this at 100 degrees Celsius. We get the equilibrium concentrations. For NO2, it's 0.0172 molar. So since NO2 is our product, we plug it in up on top. We've got it to the second power because of that coefficient of 2. And then for our N2O4, we've got that equilibrium concentration of 0.00140 molar on bottom. It doesn't have any exponent, or you could say it's got a 1 for an exponent because it's got a 1 for a coefficient. And other than that, nothing too fancy. Remember, we don't have units in an equilibrium constant expression, so our answer comes out as unitless. Okay, so again, as long as we keep this at 100 degrees Celsius, it doesn't matter what our initial conditions are. So this is a data table that I just stole from the book, and I've stolen a lot of stuff from the book, don't tell anyone. But this gives us a whole bunch of different initial conditions, starting out with this much N2O4 or this much NO2, and then letting the reaction go and seeing where we land. And aside from some experimental error, we land at about the same place every single time. Okay, the equilibrium settles out. We don't always land on the same concentration for N2O4 NO2, which makes sense. If I start with more reactant, I'm going to make more product, even if my reaction leans more towards the left side, the reverse reaction, rather than the forward reaction. Okay, the ratio of reactants to products comes out the same, and therefore our equilibrium constant comes out the same. That's why we call it an equilibrium. It's stabilizing at a certain point, all right? And if we disturb that in some way, it goes back that way. Okay, so we can plug in any concentration at equilibrium and see where it takes us. Okay, so the Kc value can tell us a little more than just, oh, this is the ratio of products to reactants in this, especially because the way that the equilibrium constant is set up can sometimes make it unclear exactly how these are connected. It's not as simple as looking at a reaction saying one of these makes two of these, or three of these makes one of these. It gets real complicated with the math here. So we will end up talking about this a little bit. Okay, here we have a couple graphs kind of using some of the data on the previous slide kind of extrapolated out. So important things to kind of pick out here. I'll say this again and again and again, I'm a broken record. The concentration of one chemical in here is not equal to the concentration of another. Same thing would go for partial pressures. Equilibrium doesn't mean we have equal concentrations. It means that we have equal rates of one reaction to the other. So the forward reaction is just as fast as the reverse reaction. And the equilibrium constant, or the reaction quotient, the K or the Q that we calculate, is that ratio between them based on that setup from the reaction. We don't really look at the individual concentrations. We look at the relationship between them. Okay? And again, even though we wind up with kind of different ending points, different concentrations, again, that ratio between them that gets us the equilibrium constant that's the same across these two experiments. As long as they're done at the same temperature, that ratio between the products is going to be the same. Okay, so if we go and change the temperature, that is going to change the equilibrium constant, just like we would see with reaction rates and rate constants. Okay, this is an example of kind of plugging in numbers for calculating an equilibrium constant. So just to kind of do the quick and dirty of it, this is kind of one step above just giving the equilibrium concentration, since this gives us the moles of gas of each of the reactants and products, not the concentrations of the partial pressures. So if we needed to, if we had like a total pressure of the system, then we could do a little, okay, well, I've got 0.1908 moles of CO2 out of how many total moles of gas, what fraction of kind of moles is that in the total pressure. So this is the partial pressure of just CO2. But in this case, they're asking for the Kc, so we're doing concentrations. We know how big the container is, and they're all in the same container. So we take the number of moles of each gas, like CO2 and H2 and CO and H2O, and divide it by our 2.00 liters that are kind of containing our gas to get our concentrations that we plug in. A lot of times we do concentration with moles of a solute divided by liters of a solution? Well, I mean, we are kind of dissolving these gas particles in a solution of gases. So, still works. So we can do a concentration for these guys and plug it in. Again, products over reactants. This one's kind of nice because we've just got ones across the board for our coefficients, which means all of these are to the power of 1. And everything is a gas, which means it is free and clear to go in the equilibrium constant. Don't forget that we keep out solids and pure liquids. Okay, so we change these guys over to molarity, again, by dividing by 2.00. Doesn't show up for these three, but we do the same thing here. All right, and then we just plug it in. We put our products on top, so our CO and H2O concentrations go up on top here, and then our CO2 and H2 concentrations are down here, and then we calculate it out. Okay, again, the value of this is going to mean something more than just, oh, it's the ratio, it's the relationship. Because right now, if someone just says, hey, the Kc of this reaction is 4.9 times 10 to the negative 3, well, that doesn't really tell me much about the reaction's relationship between the products and the reactants, unless I think a little bit further about how this is set up. What would it mean to have a number kind of very much less than 1? Okay, this is another example. I think I played this one out. I put it up on the whiteboard and kind of worked it out. But this is an example of where we use an ICE table. So initial change equilibrium. If we're not just given all equilibrium concentrations, we use how much one of these guys changes by to figure out how much these guys should change by. I know how much product we are left with, but I don't know how much reactant is in here. And there should be some left. This is an equilibrium. This is a reversible reaction. There should be some reactants still in there. So if I want to be able to figure this out, I have to plug in the concentrations at equilibrium. Otherwise, this doesn't mean anything. I lose the same amount of moles of this stuff, so therefore the same concentration. These two guys, minus x, and however much I lose, I gain in product. Well, 0 plus whatever is just 0. Plus that number. Whatever that other number is, we add to it, it's just that. Okay, so 2x is going to be equal to this number. 9.35 times 10 to the negative 4th molar. All right. So if I know what x is, I know what to plug in up here, right? So all I have to do is take my initial concentrations, subtract out the concentration that I lose to get this reaction to reach equilibrium, right? And then I've got my equilibrium concentrations. We're free to plug these in now, okay? We've got our concentrations of our H2 and our I2 and our HI at equilibrium. So all I have to do is plug them in down here. Okay, so 1.87 times 10 to the negative 3rd squared divided by 6.5 times 10 to the negative 5th times the 1.065 times 10 to the negative 3rd. Make sure you don't type that in all in one string as this divided by this times this. Otherwise, it will divide these two and then multiply that. I would multiply these first and then divide by it. Or say this divided by parentheses, those two multiplied together. We should wind up with about 50.5. And then I think my answer came out to about 50.5. If you do some significant figures, this guy only has 2 sig figs. We only have 2 kind of numbers that are shown there that aren't zeros. Stepping out, we're not showing extra zeros after it, so we just got 1, 2 sig figs for our 6 and our 5. So our answer should only have 2 significant figures. So 50.5 gets rounded to 51, so it only has 2 significant figures. And if you'd like to try it, this is another example. All right, you can kind of figure out the Kp. All right, so instead you're using pressures instead of concentrations, but it works the same way. Okay, so this is something I've been kind of hinting at, and I think I've mentioned it in videos kind of place to place, but the value of the equilibrium constant, how big or small it is, actually tells us quite a bit too. Since we're looking at a ratio of strictly products over reactants, that has to mean something. So no matter which reaction we're looking at, it's not like, okay, well, maybe we put the products on top this time, maybe we put the reactants. It's always going to be the products on top. So we would expect that the bigger the number we get, that comes from having either a very, very big number of products up on top or a very, very small amount of reactants on bottom. And that's what this is kind of showing over here. So if we wind up with a high concentration or partial pressure of products and a low concentration or partial pressure of reactants, well, that's going to end up with a number that has something much bigger than the stuff on bottom, so our answer is going to come out big. So if I do not see, let me if I don't see this stuff, oh, this would take forever. Well, you get the idea. If I didn't see this stuff and someone just told me, hey, the Kc of this reaction is 4.56 times 10 to the 9th, I'd be like, whoa, man, we're churning out a bunch of products, okay? Because our stuff on top that would give us that really big number is going to be this. Or even if our concentration on top isn't a big number on its own, it is much, much bigger than the one on bottom, okay? So the farther we get away from 1, the higher up our number goes. That means that our equilibrium is lying to the right, which essentially means this. We have products predominating the reaction. We don't like to say that we have more products because that gets a little messy with the math. If I had an equilibrium constant expression that had something squared up on top, and then I had just a concentration of something else over on bottom, like our N2O4, let's see if I can squeeze this in there, N2O4 and our NO2. Well, I could have the same concentration of these guys, but my K value would come out way bigger than 1 because this is squared up here. So, it's kind of a weird thing here. So we say that the products predominate because it's not necessarily going to mean that we have more of the products. It's not going to mean they have a higher concentration. It just means that they're kind of winning out on the equilibrium. Our equilibrium is lying to the right. Okay? Opposite goes for if we have a very, very small number, something times 10 to the negative 3 or the negative 5. We have a decimal. Something lower than 1 means that our number on bottom is going to be kind of winning out, so our equilibrium lies to the left. The reverse reaction is kind of more potent. We are pushing more towards forming reactants than we are towards forming products. So again, we say the reactants predominate. Right? And again, broken record, reverse and forward rates are at equilibrium, not concentration. So it's not like, all that. Okay. So we've got a couple examples that I've got throughout kind of this set of slides, different reactions that already have their K values laid out. So for anything that is lower than 1, in other words, a decimal, a point something, 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 those guys are going to have a large number of reactants on bottom. So like this guy right here is a small number, value-wise, magnitude-wise, which means we've got some big reactants, some value below that is huge, and then on top of our expression, we're going to have small products. Oh, I wish I could write better with a mouse. Products. There we go. Same thing here. Not as big. It's not like, oh man, we got like a way, more kind of high magnitude of reactants compared. It's pretty close to 1, so it's not that big. But we do still have reactants predominating in both of these cases. So let me do react for reactants. Reactants. And that means our equilibrium is lying to the left. Right, going in the reverse direction. Now remember what we say about equilibrium. That doesn't mean that the reverse direction is going faster. We do still have to be going at the same rate as the forward reaction to be at equilibrium. And this is what makes equilibrium kind of tough. What does it actually mean? Well, it means that we are making a greater kind of effort on the ratio to push out reactants than products. Okay, let me erase this guy. There we go. Okay, if we look at the other two reactions here, 6.5 times 10 to the 2 and 4.56 times 10 to the 9th. Oh yeah, okay. So yeah, so we're definitely pushing towards our products. So products, prod for products, predominate. Prod products. And we lie to the right in the forward direction. Right. All right. So if we were to look at these reactions individually, we could say, okay, maybe I don't have the actual concentrations of each thing, but I can see that my reaction lies over towards the reactant side. Okay, now this could be good for me if, say, I'm trying to minimize the amount of products I get. Maybe this is a chemical reaction I don't want happening in my lab, or out in kind of the everyday world. Maybe this is a product that's going out on shelves and I don't want my stuff to be making these products for some reason. Carbon monoxide is poisonous, and so is NO2, and N2O4 really isn't good for you either. But maybe I don't want these to happen. I would want a reaction that has a very, very small, less than 1 equilibrium constant that shows that even though I am going to make some of this stuff, I'm going to keep most of my reactants the way they are instead of letting the reaction kind of drift over to the right. Okay. Otherwise, if I've got something like this, where I've got a big equilibrium constant, I am churning out a lot of product, and these guys are predominating, which is good if I'm trying to sell that stuff, or if I'm trying to make it, if I'm trying to convert something dangerous into something that's not so dangerous. Like this NO is not good for us, not good for the environment, but if I can react it with some H2 gas, I can turn it into N2, which is inert and harmless, and water, which is also pretty darn harmless to us. Okay, so I might want a reaction like this to have an equilibrium constant that is larger than 1 to push in that right direction. Okay, let's say I am studying a reaction, looking up something in a reference book, or I'm typing something in online. I've got this reaction in mind, and I want to see if it is effective at removing a dangerous chemical from the atmosphere. It's a greenhouse gas, or it's toxic, it's destroying the ozone layer, it's doing something bad. So I want to see if the equilibrium of this reaction is favorable towards keeping this bad chemical out. I want to try and get rid of it. So I go and look up the equilibrium constant for this reaction. And I find something that's close. I find the equilibrium constant for the reaction, but turned the other way. So the way that I'm writing it, my forward reaction is their reversed reaction, and their reversed reaction is my forward reaction. Okay, well, I don't have to be like, well, I guess I give up. I can modify the way that I write a reaction to modify the equilibrium constant with it. And we kind of did something like this with Hess's law. When we did thermodynamics, we had reactions and be like, okay, well, I need something like this to fit, but I need everything to be doubled. So we go through and double everything, and all I have to do is double the enthalpy value to go with it. Or maybe it's like this case where my reaction is backwards from what I want it to be. So we flip it around and we just take the enthalpy value, the enthalpy change this with it, and we turn it negative to show that we turn the reaction around the other way. Well, we can do stuff like that with equilibrium constants as well, but it's a little bit trickier. It's not so intuitive. So we're going to talk about how we can do that. So there are going to be kind of 3 main ways that we can modify a reaction that modifies the equilibrium constant in a way that we can predict and easily do ourselves, okay, instead of trying to calculate it from scratch. First thing, we can reverse a reaction like I was just talking about. Okay, instead of flipping the sign on it, our equilibrium constant is inverted. So it's like 1 over whatever our equilibrium constant was. Okay, we can also multiply through by some factor. Like I said, we could double a reaction or triple it or quadruple it or something. But instead of tripling or quadrupling the k, we raise it to that power. So if I go through and double everything, I want my k to be squared. If I triple everything, I want my k to be to the third power. Okay. When our reactions are kind of crunched together, I take one, I take the other, and I kind of squish them, I cancel stuff out. Then instead of just adding up the K's like I would add changes in enthalpy, instead we multiply them. It's the product of those K's for the reactions that are added together. Okay. Finally, whatever we do with K can be done with Q also. So all these three things can also be done with Q. And we really haven't talked about Q much, the reaction quotient. Don't worry, it will be important. It will come up later. But for now, I want us to just kind of get used to how we write out the equilibrium constant expressions and what they mean. If that stuff makes sense, then the Q step is going to be easy. So we'll kind of touch on that a little bit later. So let's just look at some examples. Okay, so here is our first example. We're going to reverse our reaction. So I've written this out as the dissociation of hydrofluoric acid. So this is HF, and it's breaking up into H plus and F minus. Okay, so I go and look up the K for this, the Kc, and it is H plus and F minus up on top, my products, over my reactants. Okay, well, I've got an equilibrium constant of 6.8 times 10 to the negative fourth. If I want to flip this around and say, what's the equilibrium constant for these two things coming together and making this kind of as the forward direction, then if I flip the reaction around, this on the right side is now my products. Actually, let me do colors. So I think I said that blue was products before. So product, when before it was a reactant. So now I'm going to want HF on top. Okay, whereas my reactants are the H and the F. Cations. I'm just going to put react for reactants. Okay. So essentially, what used to be our products is now our reactants. What used to be our reactants is now our products. So this is upside down. So if we flip it upside down, we should get the same thing as if we flip this upside down. So if we just kind of put this little imaginary 1 underneath here, our new equilibrium constant for this reaction that's been flipped around should be the same as what the K is kind of flipped upside down, okay? 1 over whatever this is. So I should expect this to be 1 over my 6.8. 6.8 times 10, that's bad, 10 to the negative 4. Okay? And hopefully that makes sense. All right. Now let's say I go through and I multiply everything. So I take this NH3 plus H2O turns into NH4 plus and OH minus. This is a basic kind of reaction. Our NH3 takes a proton from water. We end up with more OH minus. So this is kind of an acid-base thing going on here. Okay, so we have this all multiplied by 4. For some reason, it just lines up that way. I just want it to be multiplied by 4 all the way through. So I don't take my old equilibrium constant and just multiply it by 4 because these are my coefficients. And what do we do with coefficients? We put them up here. Right? They are exponents. So if I were putting these as exponents, and I'm doing it for all of them, I'm multiplying through by the same thing on all of them. Oh, I didn't mean to erase all of it. Oh well, that's okay. Then that's like saying I'm taking the whole thing and I'm putting it to the power of 4. or 3 or 2 or whatever you're multiplying through by, which means I'm just taking this and putting it to the 4th power. So my new equilibrium constant to represent this reaction the way I've modified it should just be whatever my old equilibrium constant was to the 4th power. So hopefully you're seeing that these are not processes that you need to memorize necessarily. If you really need them, you can figure them out again. It's not like we're kind of breaking some math rules to get this to work, or we're doing something that's past your pay grade or your math understanding. This is all stuff that we can get. It's following the same rules that we've set before. We're just now messing with the equation that we started with, and our new equilibrium constant should work the same way. So rather than having to worry about trying to change these concentration values on the inside, we just cut to the point and say, okay, this was my original equilibrium constant. I can get the new one for this reaction if I just put it to the 4th power, and so on and so on. Okay, so there's kind of everything mathed out. So we take 1 over our old equilibrium constant. On this one, it turns out to be 1.47 times 10 to the 3rd. You may also notice we went from something that used to be less than 1 to something that is now greater than 1, which hopefully makes sense. Since we are looking at this reaction backwards, if in this reaction I had, let's see, a very small number, that means the products versus the reactants, I have a really small number, our reactant is kind of winning out. So my reaction lies to the left. If I'm turning it around, that means my reaction should lie to the right, towards the HF again. Okay, so, and that's what this equilibrium constant shows me. I'm just going to put a lot of squares around things, so it makes sense. Okay, I can also compare this guy here. If we are putting everything to a greater coefficient in here, we also push our kind of concentrations further. So whatever direction we were going, like in this case also lying to the left towards our reactants, means we're going to push even further towards the left as we raise our stuff to a higher coefficient. Okay, if we were to do something like a half, we would see it kind of go the other way. It would lessen that change, but we're still going in the same direction. It's not like this suddenly will turn and be a products dominated reaction. Okay, now this is the kind of the most confusing one, I think, especially because we're going to kind of combine it with a couple other things. So here's what's going on. Do this. So I've got a reaction here. That's one we saw before. So HF is breaking up into H plus and F minus. And I've also got this guy right here. I think this is oxalic acid. Got H2C2O4 breaking up into two H pluses and one of these C2O4 2 minuses. Now I want to know the equilibrium constant for this reaction down here. Let me switch to purple so it matches. Gotta have my color coding. Okay, so I want to know what the K of this is, but I don't have any of the data on this. I haven't run this reaction with the concentrations of each of these together. All I know is these two separately. Some bad asterisks in there. Okay, so the only way I can get this K here is to manipulate the K I have for my first reaction and the K I have for the second one. Now, if I just try to squash these two together, I'm not going to get what I want. So let's see, HF, well, that's good, I've got it, but I need a second one to match this 2 here. Okay, H plus is not in here at all, so I guess that has to go away. So I want that to go. F minus is here on the product side, but also I need to have 2 of them. So I should probably have 2 of them here too. 2 HFs, 2 F minuses. I should probably also have 2 H pluses just so I can keep everything consistent. Okay, And if I look at this other reaction, so H2C2O4 is a reactant, but I want it as a product. Okay, so it's on the wrong side. So I need to flip this whole reaction around. And hopefully that way my two H pluses will be over on the left. So they'll cancel with these guys. And my C2O4 will be on the left side with the reactants where I want it to be. Okay, so that's kind of what I'm aiming for. I'm going to have to multiply this through by 2. And I'm going to have to turn this guy around. Okay, well, I can do the kind of changes to those K's already. We already talked about these two, so let's do them. And then we can squash our reactions together. Okay, so if I want to figure out these two guys so that I can figure out my new overall K by squashing these two together, I'm going to need to kind of manipulate these first so I can make this equation. Oh, my rectangles are getting worse throughout the day. Okay, so for this one, I am multiplying everything by 2. My HF and my H plus and my F minus. So my new K for this reaction is going to be to the second power because I am multiplying my reaction through by 2. Okay? This one, since I'm turning it around, I don't just take the K and make it negative. That doesn't really mean anything. What I need to do is show that I've changed signs for the products and reactants. So if my products are now my reactants are now my products, this should be inverted. It should be flipped over. So these guys would be turned over upside down, which means my K value would be turned upside down. So 1 over this K value is going to be my new K here. Okay, so I can get these two new K values. All right, so let's see what those numbers become. All right, so I take this to the second power. I get 4.62 times 10 to the negative 7th. Great, awesome. I also take this one and invert it. I get 2.63 times 10 to the 5th. Also great. And now these reactions should be able to come together to make this one down here. I don't know if I keep drawing rectangles, they're just going to keep getting worse. So let me take that one off of there. Okay, so I get 2 HFs, which is what I have down here. I get my C2O4 on the left. I get my H2C2O4 on the right on the products, along with my 2 F minuses, which I have over here, and my 2 H pluses cancel with these 2 H pluses. Okay, I've got these guys on the product side, I've got these guys on the reactant side. So I get this reaction that I wanted. So all I have to do is squash these two together now. So I've got my new K for my first reaction, my new K for my second one. To get my new K overall for these, whenever I add reactions together, I multiply my Ks for each reaction involved. So I'm taking this times this, which is what we're doing down here. My red reaction times my blue reaction's Ks. Okay, so I take this times this, I get about 0.122. And I get the K for this new reaction. I don't have to, again, know anything about the concentrations of this original reaction as long as I have Ks to manipulate, just like I manipulated these reactions to get the reaction that I wanted. Sometimes we deal with an equilibrium constant that is already calculated for us, but we are trying to figure out the concentration or partial pressure of a specific chemical or two at equilibrium. So we already have the value. We know, okay, I've got this reaction. It's at 100 degrees Celsius or 25 degrees Celsius or something. I've looked up and I've found the Kp or the Kc. I want to know how much N2O4 or NO2 or CO2, H2O, something is available at equilibrium. How much is going to be floating around? So these calculations get a little bit trickier, but they do also take a little bit from some tricks we've learned before. So this is an example that I've got worked out separately, where we've got the N2 plus H2 making NH3 and going back the other way. It's a classic. We've got a Kp value of 1.45 times 10 to the negative fifth, specifically when this temperature is right at 500 degrees Celsius. Okay, so we've got the partial pressure of our H2 and our N2 when we are at equilibrium. This guy, we've got this guy. But we don't know the partial pressure of our NH3 at equilibrium. So to figure that out, we've got to get a little tricky. Now, before when we had some missing stuff, we did an ice chart. I for initial, C for change, E for equilibrium. And then as long as we know the initial of one chemical and the equilibrium of another, we can figure out how much the change is. Or we might know the change and the initial, so we can figure out what the equilibrium is. Or we could do another variation where we have the change in the equilibrium and figure out how much did we have originally of this. So in any of these cases, we kind of need two of these pieces if we want to figure out the third. A lot of our math-based stuff is kind of based on that. We need to have only one missing piece of information. So if we wanted to do an ice chart, we'd have to have something like this. Now in this case, we have two equilibrium pressures. So let me erase. Oh, come on. There we go. Erase some of this. So this is what we have. I've got our N2's partial pressure. We've got our H2's partial pressure, both at equilibrium. And I want to know what this is for my NH3. But I don't know what we started at, and I don't know what our change was. So to get here, and here, and here, we've got basically no information. So doing this with an ice chart is going to be impossible. We're not going to be able to do that. So instead, we're going to have to get a little bit crafty with this. So this reaction is one we saw before. It's the synthesis of ammonia. You might see it called the Haber process, or Haber. I'm not trying to pronounce it. But anyway, N2 plus 3H2 makes two NH3s, and also back the other way in that reversible reaction. In this case, we are looking at this at a different temperature than before, which means we have a different equilibrium constant, even though we're still doing this with Kp's. Okay, so at 500 degrees Celsius, our Kp is 1.45 times 10 to the negative fifth. So having a different temperature has given us a different equilibrium constant. That means that our reaction doesn't sit the same way when we're at a different temperature. So there must be something a little bit different about how the reaction moves as the temperature changes. So we can assume that since our Kp is a very small number, it's less than 1, that means that our, what is predominating? Well, if it's a small number, then the stuff on the bottom is going to need to predominate, and we're doing products over reactants. So our reactants must be kind of predominant in this reaction, where our products are kind of an afterthought almost. We have way more of this residing compared to how much product we actually pump out. Okay? But if we want to know the actual pressure of the product that we're making, we're going to have to solve for it. Okay? So we've got our Kp value already given to us this time. So we're not calculating the Kp. Instead, we're going to use it to figure out this concentration here. So let's lay out our Kp setup with our products over our reactants. Okay, so we've got our equilibrium constant expression laid out. We've got our products on top, our reactants on bottom. Okay, now since we are given these partial pressures of the N2 and H2 at equilibrium, we can just plug those right in. So let's do that. We've got a pressure of 0.432 for our N2. And a pressure of 0.928 for our H2. Now, again, realize that I've dropped my atmospheres, so I'm not just being lazy this time. We don't want units in our Kp expression. Okay? And I'm still missing this pressure up on top. So we could call this X or a question mark or a square, whatever you want to do, as long as you know you've got to solve for this. I'm just going to make it an X, just so, not super creative, I guess. All right. Now, something we need to be careful of, okay, is I am solving for the X, okay? I'm not solving for the top, okay? Because there is this squared here that comes from the coefficient out front, okay? So I'm going to need to undo this at some point to get this to work out, okay? So this is great and all, but I can't solve this as is because I've got this, X, and I also don't have a Kp value written out right now. So I also need to set this equal to the Kp value that we've already been given, so I have, only one variable to solve for. So let's write that in. Okay, so if I can find the right value of X, that should make this whole thing equal 1.45 times 10 to the negative fifth. Okay, so since these are just numbers down here, I can kind of work out the math there and put those together. So let's do that first. So I'm going to take 0.432 times 0.928 to the third power. Okay, the bottom of this should be equal to about 0.345. Okay. Again, I'm still solving for the X, and just so it doesn't get confusing, I'm going to erase this here so it doesn't feel like we need to solve for it or something. Okay, so if I'm trying to get the X alone, I've got to get rid of this. So I'm going to multiply it over. So I'm multiplying both sides by 0.345. There. Those will cancel. Multiplying it over on this side. Okay, those are just two numbers, so I'm going to go ahead and multiply those two. Our 1.45 times 10 to the negative fifth times that 0.345 gets us about 0.0000501. Right? In scientific notation, we can also rewrite that. To get past that first actual digit, we've got to move 6 spots to the right. Okay, so we want this times 10 to the something 6, either positive or negative. Since this is actually a really small number, we want it to come out small with the scientific notation. So we can rewrite this as 5.01 times 10 to the negative 6th. Okay, last step. If I want to know the partial pressure of my NH3, that's what I'm solving for as I'm going for X. So I've got to square root this thing. Square root the left to undo the square, and I've got to do the same to the right. And then I've just got to look at my calculator and punch in this square root of 5.01 times 10 to the negative 6th. Again, don't forget to put parentheses around the whole thing when you type it in. Okay. Square root of parentheses 5.01 times 10 to the negative 6th. Close parentheses. All right. I've got about 0.00224-ish. Okay, and since I want to know the partial pressure of this, and I know it's supposed to be in atmospheres, I'm going to tag the unit back on so I can write it as a pressure. Okay, so my pressure of just the NH3 gas at equilibrium is going to be 0.00224 atmospheres. Or, again, you might rewrite this as 2.24-ish times 10 to the negative third atmospheres. Now, here's something that you might want to be careful of when you look at problems like this, okay? Because it's easy to jump the gun and think you have like a quicker way around that might get you into trouble. So, if I were looking at this and I weren't thinking in terms of equilibrium, and I was told, okay, we've got these two pressures at equilibrium, we need to find this pressure, I'd be like, oh, okay, one of these makes two of these. So if my pressure over here is 0.432, I just double it, and then that's going to be the pressure over here. Except that's making some assumptions. First off, that we would be moving in a complete forward direction, so that all this would make all of that. And it also wouldn't make sense if that were true, because if all of this makes all of that, then there wouldn't be any of this at equilibrium. So I can't do that. Okay? Now, I also can't even assume that the ratio holds true just across these two. So if I'm looking at like this guy and this guy here, if this were holding up to kind of the stoichiometric kind of relationship at equilibrium, then 3 times as much of this should be equal to this. So if I take this 0.432 and multiply it by 3, I should get as much H2 as I would need to react with that. But that would be if we had the perfect amount of reactants to make some perfect amount of products. And that doesn't have to be necessarily true. You know, we could pump in as much N2 or H2 as we wanted. Or we could even pump in some NH3 to start the reaction, and then let it settle to equilibrium. So just because we have an equilibrium doesn't mean that every chemical is being used in the right stoichiometric ratios. Okay? The equilibrium is a ratio of the partial pressures of the concentrations once the reaction settles out. But that means there could still be excess in your container. Okay? So the reaction will shift back and forth, okay, to reach that equilibrium, but we can't make some assumptions about how some of this will be equal to this or that or the other thing. Okay, that's why we have to go through this mathy stuff. We're not just like, oh, we haven't done algebra in a while and throw that in. Okay, we're not going to torture you if we don't have to. Okay, now we did see something kind of like that with the ice chart. Okay, that's initial change equilibrium. It looks something like this. And like initial change equilibrium. Okay? Where if I knew how much I started out with or how much I ended with, I could write those concentrations or pressures there, all right? And the change would be some kind of plus X thing for the reactants and some, some minus X for the reactants because we're using them up. And some plus X thing for the products. And we would use the coefficients to describe kind of how much the change was. Oops. Okay, so if like this is my N2, this is my H2, this is my NH3, then if I'm looking at how much something is going to change, kind of make some room here, then yes, I would be able to say the stoichiometric kind of relationship matters because I can't have the reaction happen without following that setup. Okay, but that doesn't mean that the reaction has to start or end that way. Okay, so the change can be related with x's like this. Okay, the actual initial concentration that we have or the equilibrium concentration that we have can't be done that way. So be careful about where you kind of throw around your x's and 2x's and 3x's, or where you just plug in what you can and solve with the kp or kc. Okay, it makes it kind of difficult, but just remember, you can use an ice chart if you can figure out how much of a change is going on. Okay, from the initial to the equilibrium, or if you know how much the stuff is changing by. Okay, but if you're only stuck with all equilibrium concentrations or something like that, then we don't want to bother with an ice chart. Okay. They also show that you can plug this back in with the partial pressures that we knew for sure to make sure that you get this equilibrium constant that we were already told is there. There's another example down here you can try for yourself. It's already got the answer there. You can see if you can reach that answer. We're trying to find the partial pressure of Cl2. Okay. And this is another example. We've got NO and H2 in a reversible reaction with N2 and H2O. So we set up our products on top, our reactants on bottom, and then we work it out from here. Okay, and in this case, this is a time we can use an ice chart to help us out. So let's see. We've got some initial data for the concentrations of NO and H2, N2, and H2O. So we know what everything is starting at, which is kind of nice. And it's also pretty necessary. We also know what our NO concentration winds up being here. So initially a mixture of 0.1 molar NO, 0.05 molar of H2, 0.1 molar of H2O is thrown in, which is what we had down here. You may notice that they also say there's no N2. Sometimes I can see them making problems where they say this is what we put in, and if they don't say something is added, that means there's none of it to start with. So it's like they're throwing kind of the ingredients in and letting the equilibrium figure itself out. So we're not including one of the products. So in that case, your pressure or your concentration would be 0 to start with. Okay, at equilibrium, the concentration of NO is found to be 0.62 molar, sorry, 0.062 molar, which is why we get this down here. Okay, so we know the before and after for this reaction. A change happens, and if a change happens in this reaction, it has to follow the stoichiometry and the coefficients of this reaction. Okay, well, my rectangles aren't too bad now. So if I am making this reaction run, and I'm going to end up with some amount of N2. Since I didn't start with any before, I've got to make some. That means I've also got to make some other of this product. And to do that, I've got to use some of this. So my NO's concentration, or its pressure, is going to go down. H2's pressure is going to go down, or concentration. N2 is going to go up. H2O is going to go up. Okay? And the coefficient tells me by how much. Okay? So you got a 1 here and a 2 here. So you can think of this as basically we're losing 2 times as much as NO as 2 times as much of H2 as 1 times as much of N2 that we're gaining and about 2 times as much of H2O that we're gaining. Okay, so however much our NO decreases by should be the same as the H2 decreases by because their coefficients are the same. Minus 2x minus 2x kind of goes the same pattern. Okay, so this is going to drop by the same amount. Okay, our H2O is going to increase by that same amount. and our N2 is going to increase by half of that. Okay, so to get from 0.1 to 0.062, we're losing 0.038 molar concentration. Okay, so we lose 0.038 molar concentration for that 2. We increase by that much for H2O, and we increase by half of that for this guy, since it is an X instead of a 2X. Okay, so we just go and subtract, we add, and we add, and we get our equilibrium concentrations. Now, finally, we can go and plug this all in to calculate our K value. So this is a case where we are figuring out the equilibrium concentrations, and we don't have the equilibrium constant to help us. All right, so the ice chart helps us out instead. Again, initial, change, equilibrium. All right, last example I'm going to show. This is for Kp. Okay, so hey, it's a classic N2O4 makes 2 NO2s and vice versa. So in this case, the way it's written, our products are the NO2 that's on top. The coefficient of 2 means it is squared. And then we've got our N2O4 for our reactants on bottom. Okay, we are told that we are starting with 3 atmospheres of dinitrogen tetroxide, that's this guy, and 2 atmospheres of nitrogen dioxide, that's this guy, at 25 degrees Celsius. So we have a little bit of this and a little bit of that. Okay, we're letting it reach equilibrium. The pressure of the nitrogen dioxide decreased by 0.952. So in this case, we know the change of one of these. Okay, so if our NO2 decreased by this much, okay, that means our N2O4 has to increase by some amount related to that. Okay, so if I am using some of this NO2 to make some of this N2O4, again, it has to follow this stoichiometry. So I'm losing 2x of this to make 1 regular x of this. So however much I lose from my NO2, I am gaining half as much as what I lost. So 0.952 over 2. And if that part's still confusing you, maybe I can write it out a better way. So my 0.952 that I'm losing, the negative 0.952 that I'm losing, is equal to the 2x that I've stated over here for my coefficient. Basically, whatever the coefficient is, you just stick in front of the x for your ice chart. Okay, if I go and solve this out, I want to divide both sides by -2, divide both sides by -2. So the x that I get is this positive 0.476, and that's what we're using over here. Okay, so if we started with 3, we add 0.476 to that to get this equilibrium pressure. All right, and we lost the 0.952 from this guy, so we subtract that out to get this equilibrium pressure, and then we're just plugging it in from there. Okay, and in this case, this is a time we can use an ice chart to help us out. So let's see, we've got some initial data for the concentrations of NO and H2, N2, and H2O, so we know what everything is starting at, which is kind of nice. And it's also pretty necessary. We also know what our NO concentration winds up being here. So initially a mixture of 0.1 molar NO, 0.05 molar of H2, 0.1 molar of H2O is thrown in, which is what we had down here. You may notice that they also say there's no N2. Sometimes I can see them making problems where they say this is what we put in, and if they don't say something is added, that means there's none of it to start with. So it's like they're throwing kind of the ingredients in and letting the equilibrium figure itself out. So we are not including one of the products. So in that case, your pressure or your concentration would be 0 to start with. Okay, at equilibrium, the concentration of NO is found to be 0.62 molar, sorry, 0.062 molar, which is why we get this down here. Okay, so we know the before and after for this reaction. A change happens, and if a change happens in this reaction, it has to follow the stoichiometry and the coefficients of this reaction. Okay, well, my rectangles aren't too bad now. So if I am making this reaction run, and I'm going to end up with some amount of N2. Since I didn't start with any before, I've got to make some. That means I've also got to make some other of this product. And to do that, I've got to use some of this. So my NO's concentration, or its pressure, is going to go down. H2's pressure is going to go down, or concentration. N2 is going to go up. H2O is going to go up. Okay? And the coefficient tells me by how much. Okay? So you got a 1 here and a 2 here. So you can think of this as basically we're losing 2 times as much as NO as 2 times as much of H2 as 1 times as much of N2 that we're gaining and 2 times as much of H2O that we're gaining. Okay, so however much our NO decreases by should be the same as the H2 decreases by because their coefficients are the same. Minus 2x minus 2x kind of goes the same pattern. Okay, so this is going to drop by the same amount. Okay, our H2O is going to increase by that same amount, and our N2 is going to increase by half of that. Okay, so to get from 0.1 to 0.062, we're losing 0.038 molar concentration. Okay, so we lose 0.038 molar concentration for that too. We increase by that much for H2O, and we increase by half of that for this guy, since it is an X instead of a 2X. Okay, so we just go and subtract, we add, and we add, and we get our equilibrium concentrations. Now, finally, we can go and plug this all in to calculate our K value. So this is a case where we are figuring out the equilibrium concentrations, and we don't have the equilibrium constant to help us. All right, so the ice chart helps us out instead. Again, initial, change, equilibrium. All right, last example I'm going to show. This is for KP. Okay, so hey, it's a classic N2O4 makes 2 NO2s and vice versa. So in this case, the way it's written, our products are the NO2 that's on top. The coefficient of 2 means it is squared. And then we've got our N2O4 for our reactants on bottom. Okay, we are told that we are starting with 3 atmospheres of dinitrogen tetroxide, that's this guy, and 2 atmospheres of nitrogen dioxide, that's this guy, at 25 degrees Celsius. So we have a little bit of this and a little bit of that. Okay, we're letting it reach equilibrium. The pressure of the nitrogen dioxide decreased by 0.952. So in this case, we know the change of one of these. Okay, so if our NO2 decreased by this much, okay, that means our N2O4 has to increase by some amount related to that. Okay, so if I am using some of this NO2 to make some of this N2O4, again, it has to follow this stoichiometry. So I'm losing 2x of this to make 1 regular x of this. So however much I lose for my NO2, I am gaining half as much as what I lost. So 0.952 over 2. And if that part's still confusing you, maybe I can write it out a better way. So my 0.952 that I'm losing, the negative 0.952 that I'm losing, is equal to the 2x that I've stated over here for my coefficient. Basically, whatever the coefficient is, you just stick in front of the x for your ice chart. Okay, if I go and solve this out, I want to divide both sides by -2, divide both sides by -2. So the x that I get is this positive 0.476, and that's what we're using over here. Okay, so if we started with 3, we add 0.476 to that to get this equilibrium pressure. All right, and we lost the 0.952 from this guy, so we subtract that out to get this equilibrium pressure, and then we're just plugging it in from there.